Kia ora, everyone, and thanks for attending this presentation. I decided to put together some thoughts, also some discussions with a lot of colleagues over the past couple of years on prediction and apply them particularly to shoreline modeling. In reality, I will also use examples from estuaries because some of the researchers I work with focus more on estuary and really try to address uncertainty and how to deal with uncertainties, how we're dealing with uncertainties when dealing with shoreline modeling. I want to acknowledge right from the start that a lot of this presentation was thought for a talk that I was invited to give at the Coastal Dynamics when it was held last year in Delft. But I'm actually based in Auckland at the University of Auckland, and it's a very beautiful place in New Zealand. I hope you will be able to visit soon. So in the next 30 minutes, you will hear about predictions in coastal systems. It's a huge topic, really. What was I thinking when I came up with this? I will try to make example from beaches and estuaries. And this is a topic that fascinates me quite a bit, is relevant, is important. This is the time when we have to discuss this thing. But also, since I work both estuary morphodynamic model and shoreline models, I really have some difficulties with some of the things that we do, how we do them. And so I guess I got overexcited and decided to have such a broad title. Really, predictions are what we are asked to do a lot of times together with understanding. And when I think about uncertainty, the first word that I associate to prediction is in fact uncertainty, and also a type of uncertainty that particularly fascinates me is actually ignorance. I found ignorance a great motivator for my research. If I'm ignorant about something, I want to discover if we are all ignorant about something, that's when it gets really exciting science. And I want to make predictions. So I have to deal not only with uncertainty, but in some cases I have to deal with complete ignorance. As I said, there will be examples from modeling long-term changes in coastal systems in the broadest sense. And I will try not only to generate problems, but I also want to give you a way forward and some work that is going on within my group and that I know in other groups that I think is relevant. Why do we need predictions? I don't need to spend much time to convince you that we need predictions. We know we need to be able to make predictions, and we know that we need them for coastal hazard and for coastal management. There is a huge pressure to predict the impact of climatic changes. But we make predictions also when we try to understand, when we want to improve our knowledge, when we want to prove ourselves that we've been able to understand. In fact, every model, physical, numerical in the lab, has to make testable predictions. It's our way to advance knowledge and almost win the fight against ignorance. I also wonder if making prediction is not also part of our human nature. I'm currently in groups that try to predict how many COVID cases we get tomorrow. We somehow, at some level, we enjoy predicting. I think it's because somehow it makes us feel like we understand what's going on in the environmental system we're looking at. So let's throw some definition of prediction in its broadest sense. It's a statement about the future. I also want to bring immediately the word projection and clarify the difference, because the projection is a statement about the possible future under certain scenarios. As you will see, we will need to actually modify these statements. I also like to always indicate, to associate, when I speak about prediction, I want that it's clear that we need to get better at understanding. We need to improve our predictions, and probably the way that I like the most to do that is by improving theory. I also like doing data analysis, and I think the two should work together. In fact, one thing that I did together with Anna, we started this podcast, and we ask questions to scientists around the world. And here are some answers to the core question, really, of that I have in mind. Can we do long-term morphodynamic predictions? Are they meaningful? So we started interviewing scientists, and here you can see some comments. Britt Raubenheimer just said, that was her answer initially. Then she developed and she explained that she's still a little bit skeptical of how models work. There's a lot of interesting answers in this podcast. I just took the first one that I almost remembered. For example, Andrew Ashton said, absolutely, in 50 years, we will be even better. Obviously, because he then explained, if you don't say what you want to predict, we can definitely make predictions. And the other subtle point was that in 50 years, we will get better because we have more data. Bob Guza was quite puzzled by how we are going to deal with climate change and with beaches that are not backed by dunes. There is not an infinite reservoir of sediment, but there is a seawall, or the sand just finishes and there is a rock bottom. I also like that Karen Bryan and Martin Kleinans went straight for it's a matter of scale, but modeling details is possible. This is important because depending on the scale we try to predict, we obviously have to accept what level of detail we are actually capable of modeling. And so on. Take advantage of this podcast. There are a lot of interesting words from many scientists. Anyway, the issue of prediction is that just stating what a prediction is not enough. There is a famous paper from a few years ago entitled, "You Want Me to Predict What?" Because in fact, if we make a prediction, we need to associate a spatial scale. We need to associate a temporal scale. And I think this is so important that the moment we have decided that the temporal horizon and the scale, the spatial scale we want to predict, well, then at that point, we actually probably should choose the type of model we want to use, the variables that have to be accounted for, the inputs that are necessary for this model. We don't have to necessarily start from modeling orbital velocities. Maybe if we have to move to much larger scales, we just need models that have variables defined at those larger scales. Defining what we want to predict is actually often quite complicated. And of course, we want to make useful and meaningful predictions. And to make those predictions, we need models. Models, though, are by definition the art of abstraction, simplification, reduction. And it is inevitable that as the prediction horizons goes farther into the future, uncertainty will also tend to increase. But what I want to stress is that what I'm trying to think of is the framework that we want to use to deal with all the uncertainties that pervade our modeling and so our predictions. So I will start a little puzzle, and I want to begin to discuss uncertainty. I will define almost three different axes: the location of the uncertainty, so where the uncertainty is in the model. This is probably almost intuitive. Then the type of or the nature of the uncertainty, whether it is an imperfection due to our knowledge or simply because of inherent variability of the phenomenon we are studying, another effect that propagates further into the future. And then also want to discuss about the level of the uncertainty, because when we speak about uncertainty, we move almost from determinism, we don't have determinism, but from complete determinism to complete ignorance. So I want to discuss a little bit the level of uncertainty and how that affects the prediction that we make with models. So let's put a couple of the first pieces since we have defined prediction, and let's get started with where uncertainty hides. Actually, it's probably not hiding, even it's pretty evident inside the model. So the first thing that comes almost obvious, it's boundaries. This one seems simple, but I think it's still relevant and worth mentioning. How do we close a system? For example, if we're modeling the morphodynamic evolution of an estuary, like the one that you see here, and for the record, I live right here. This is Auckland. when we try to model an estuary, where do we set the offshore boundary? It's actually something that we discuss almost at every meeting with one of my research PhD students is where do we close? Because that affects the way we can run the model, how long it takes. And in the field, obviously, of if we are thinking about beaches and shoreline modeling, a lot of models require, for example, the offshore boundary, the definition of the depth of closure. And we know that models tend to be dependent often on that parameter. When I say boundary identification, I speak about something that appears to be simple, but can actually even affect our simulations and so our predictions. Now we go to one of the big ones, the structure of the model. We might think, in fact, that most sources of technical uncertainty can be under control, but the structural uncertainty is usually not under control. And it's one of the most critical components of modeling. We still don't know which is the most useful approach to modeling. We continue to use the most disparate techniques. We don't know what is an appropriate complexity model for the predictions we are making. In fact, we don't know, should we start from orbital velocities as they do in, for example, in X-Beach, coastal Delft 3D models, or should we use more of an Ashton and Murray approach where we look at much larger scale change, the variables that we are using, and generate morphodynamic change at longer time scales? Or if I think of estuary, there are models like Asmita that directly simplify also the geometry of the system. This is a difficult point, and there isn't really a solution. What models should we use? Should we use finite difference? Should we use cellular automata? Should we use one of those super OpenFOAM, OLAFOAM, SPH models? There is a variety of structures that we can use when we develop the model. But then the model structure difference is also in how we model friction, in how we model undertow, in how we model the even tidal propagation. So this is really a big source of uncertainty. Another, before getting to the inputs, I don't want to present only a problem, so I will also try to propose some way forward. For example, one way to deal with structural uncertainty is the use of ensemble models. This is not something new because already many of us know that, for example, in meteorology, they use, in hydrology, they tend to use ensembles quite regular, but for us, it's not quite usual business. So here I have some nice pictures reminding of a workshop called Shoreshop held in New Zealand a couple of 3 years ago at this point to win this fantastic hat. And the interesting thing is that the best model was a machine learning model taken individually, but overall, really, the best model for the short-term predictions was an ensemble of all models submitted by participants. And there were all sorts of models. We were trying to model shoreline changes. So there were machine learning models, data-driven models, Shoreford models, Yates, Sean Vitusek brought his model. The best one actually was a model that was the ensemble of all models. Now, it is also worth mentioning that there are also other efforts in the community looking at ensembles of modeling. And here I just mentioned the one from the paper by Limber looking at cliff erosion using a variety of models and presenting and then studying the ensembles. And in our field, we can also think of the very recent paper, so recent that I haven't fully read it, but I know that it is important and I will read soon from Simmons and Splinter on, in fact, using multi-model ensembles. To me, it seems like this is a very smart way to look at the problem of model of structural uncertainty, where we don't know what is the right model to use, what is the right way to represent the process. Let's use a lot of models with different structures and then just average them out, possibly in a smart way. We will discuss this later on. So let's now move to other locations of uncertainty. For example, input. inputs. This is an obvious one, especially if we speak about long-term morphodynamic changes for estuaries or for beaches. There is the insurmountable problem of input data, because we are looking into the future, so we don't know the data. We have to extrapolate what we use from other people's studies. In our field, we are getting better at collecting bathymetric and hydrodynamic data, but there is not really a lot we can do when we begin to look further into the future. Predictions of sea level rise, a key input of modeling and predictions, comes with uncertainty bands. You can see it already here in these quick examples. Here we have two different scenarios, and so two different median curve for sea level rise, but with large error bands. And then, for example, when we deal with storms, when we deal with wave climate, with weather patterns, we are essentially relying on larger global climate models to finally make those estimations. So the uncertainty that we're introducing at this stage is large. And so I want to speak a little bit more about it, because we can start with sea level rise. Which scenario do we need to use? There's in a paper by Danna. You should work, if you work on shoreline prediction, you should look at the work by this recently graduated Danna in the group of Bruno Castelli. He's done some amazing work on shoreline modeling. And here, in his case, he shows the two curves that he uses. They deal with, again, two different RCP scenarios. And again, the two curves humans. Again, can we reduce this type of uncertainties? Here I show you the example of the case of waves. We are putting a lot of effort into trying to reducing this uncertainty. I believe the only approach that we can use really is some sort of emulator, developing an emulator. This is what Laura Cajigal did during her PhD. And it works on some sort of Monte Carlo approach in the end, because you emulate the wave climate, you generate synthetic time series of wave height, for example, or you can do it also for the wave period, or you can do it coupled. And then you use a simple model, usually because the number of simulations is large, where you run all the different sequences, time series of wave height. And then again, there's the problem of averaging and making an ensemble, making sense of all these predictions. Here you see the figure. We didn't use sea level rise in this study. But there is more. There is other people that have been working on this, developing different types of emulators, for example, Mark Davidson. But there are other examples in Europe and in Australia that I'm not mentioning here, but that are worth checking. There's the work of Sean Witusek that really tried to formalize how uncertainty unrolls almost over time. There's a lot of work that is getting more and more to the core of how to account for uncertainties in some of the inputs. Parameters, we also have to deal with parameters. This is the one source of uncertainty we're all immediately and always aware. Here is an example of an estuary of the type of thing that we do. We want to model the long-term evolution of estuaries, and we want to see the effect of vegetation, for example. Well, we know that vegetation clearly plays a role. Just look at the mangroves in this picture here, but how to parameterize that effect? We went in the lab and tried to mimic the effect of mangroves. Other people like Karim Bryan and Julia Mullarni, they went in the field and in the lab, and also the presentation we looked at today, looking at the effect of vegetation. We go and collect measurements at a very small scale. We try to come up with, parameterize what the processes that we see in action, and then we use those parameters for long-term predictions of morphodynamic evolution. This is obviously a large, big source of uncertainty. We tend to say that we know how to deal with these, again, with Monte Carlo simulations, but it is evident that this poses a challenge also to the type of models we can use. Here you're seeing two model runs, one morphodynamic runs of an estuary. Offshore is in the upper part, the deep blue, and here there are barriers, and here is the basin and the tidal network with channels developed, in one case with vegetation, in the other one without vegetation. So in one case with the parameterization, in one without. The effect of vegetation is huge also in the model, but it is the effect of those parameters and sensitivity to those parameters when modeling estuaries of this type is actually quite complicated, because those models it actually takes a lot of time to run. The way we do it, I will steal a slide from Maurizio Danna's PhD defense. We know the parameters that we care about, and we know the probability distribution of those parameters. And then we just sample Monte Carlo mode, run the shoreline model or the estuary model, and come up with the probability density function that describes our output. This is the way in which we can account it. And this is how Danna did it in another of his papers, this one in JGR, where he looked at the effect of coupling models that deal with fast oscillations and long-term changes of shoreline, showed the difference between the parameter sensitivity and the sensitivity to how much we know about sea level rise. Great work. I strongly suggest to have a look at his papers. For our purposes, and I don't want to keep you here all afternoon, it begins to look like a will. I also want to go ahead, and when all uncertainties pile up, we have what is usually called the outcome uncertainty. And this figure tries to show some of the effects that are in what we see in the model outputs, in our predictions. I mean, the top two panels show how the outcome differs when different grid sizes are used, using the same model. This is Delft 3D. This time, to confuse you, offshore is down. Again, I'm using an estuary morphodynamic model. This is the basin where, thanks to the tide, all these channels develop. And after the same amount of time, if I use the 25 or a 100 meter grid, results are not exactly the same. It's not unexpected, because of, obviously here I would expect more resolution, but it seems like in one case is more regular and symmetric, the pattern, than in the other, which is a little bit disturbing. But I really would like to focus your attention on this plot here on the top right and the two bottom ones. These are three different models that are trying to produce a tidal network, so only tides are the forcing. And here you're seeing the elevations, and so the channels that dissect this semicircular plane. And here it is an interesting study. We published this figure some years ago, but we are actually still working on it, trying to understand what's going on. How is it possible that when we fix all the parameters in these three models, we still get such different results? This is quite shocking in some way, and we are still working on trying to understand why this happened and what the implications are for predictions of natural systems and not of a simplified system like this one. So we have added some, we looked at some type of the uncertainty, how it manifests inside the model. Now we will quickly look at how the nature of uncertainty, whether it's imperfection in our knowledge or its inherent variability that we just cannot predict as we fill out our puzzle. There's, in terms of type, there is some uncertainty that we hope to be able to reduce again, and is related to our knowledge. It's what I call technical or numerical errors related to data measurements, model, the way we model some processes. I think this is likely to improve. Models will always be imperfect by definition, but there is the hope that we can decrease some of those technical uncertainties. But we also have to accept that there is natural variability in natural systems, and probably one of the challenges is trying to understand how natural variability limits our ability to predict. There are also other types of uncertainty that involve our need to be truly interdisciplinary, and this is valid for estuaries and for beaches that are backed by dunes, often more and more by vegetated dunes. I mentioned that we try to parameterize the effect of vegetation on morphodynamics. Well, the reality is that there is a closed loop and a feedback loop between vegetation and morphodynamics. And even more, when we think of long-term predictions in climatic change, we have to think that as vegetation gets affected by climatic changes, also the feedback loop with morphodynamics gets affected. Few studies at the moment are going that deep. But if we have to deal with long-term predictions, we know that society itself provides a huge source of uncertainty, and that societal choices will affect our coastal systems. How to predict society and the human behavior is beyond me. It's something that I would like to work on, but it seems to me something that casts a shadow on the type of predictions that we are doing. And a similar argument can probably be made for technology. We are becoming better and better at moving sediments on the dunes or modifying our estuaries. And certainly technology will play a big role in how we protect our coastlines in the future, I suspect. So, and now even more rapidly, I now want to spend a minute discussing the level of uncertainty, which more or less I think of in terms of how ignorant are we. We would love to make deterministic predictions for the long term, but let's forget about that. That doesn't exist. Determinism doesn't even get a box in this arrow here, because determinism is really not what we need to do when we deal with long-term predictions. But really, I go back to the fundamental questions. In light of what I said so far, how useful can long-term predictions be? Well, let's see how we make those predictions. Our predictions are based primarily on our limited knowledge and our parameterizations, well, then in that case, we can speak about the lowest level of uncertainty, what is called statistical uncertainty, where statistical predictors directly, in a way, through the use of data, allow to explicitly address uncertainty. And we can also do the classical sensitivity analysis, run the model with Monte Carlo mode. But there are also cases when multiple equally plausible alternative futures are present. In this case, for example, when we begin to deal with sea level rise and the fact that we don't even know which scenario for sea level rise we're using, that's really the zero order ingredient. Well, then at that point, we are really dealing with scenario uncertainty, and we are doing scenario modeling. So I think a lot of the work on long-term prediction actually falls here, before that fascinating part that is the recognized ignorance we have to face at some point. As we increase the level of uncertainty, we have to face ignorance, or people call it deep uncertainty or unbounded uncertainty. These are cases where we recognize that we just don't know enough. For example, I don't think we recognize that our understanding of basic sediment transport is still limited. But there are also other questions that we pose. Is our equilibrium model, is equilibrium in a shoreline model a reasonable hypothesis? Can we model estuaries in 2D depth average mode or in 3D mode? There are some of those, we just don't know what is the best thing to do. And again, the only way we can somehow address this is to, on one side, by trying with different model structures, and another one is to discover how those natural system works. And the topic of discovery is obviously closely related to ignorance. And even if it's not related to long-term morphodynamics, I want to show two little results from students recently graduated from my band that looked at that discover things that we didn't even imagine when we started. We did some laboratory experiments on the formation of edge waves, and all of a sudden we discovered that randomness in the waves causes intermittency in edge waves, something that was not even thought in the theory yet. Or similarly, Chuan Jin did his model of hydrodynamics over equilibrium ripples to discover that actually equilibrium ripples are unstable and can generate hydrodynamic instability called ribs. So there's room for discovery. It seems to me like we still have to agree or discover something that can help us to deal better with long-term predictions. Okay, we're almost completed our puzzle. Before we complete it, I want to fix the definition of prediction and projection that I gave at the beginning. There is no need for me to read about the definition, but I go straight to the point, and we need to move beyond the individual deterministic predictions that a lot of times we've been doing. A prediction, in fact, should be not a statement, but a probabilistic statement. It is actually worse because I think we have to change also the projection with idea, and also the projection is a probabilistic statement about possible future under certain scenarios. Because we are dealing with climatic changes and we really have a number of sources of uncertainties that at the moment we really don't know how to deal with. Let's keep in mind that when we speak about parameters, we are also talking about something that will require a monster amount of simulations, coupled with the input, the uncertainties in the input. We are building more and more a real monster, a monster that has got a lot of tentacles, the inputs, the boundaries, the structure of the model, but it's definitely a tough fight, the one that we are facing. Okay, now I want a little bit of a digression, just a couple of minutes, because data is super important, and you hear machine learning almost every day. 95% of existing data has been generated in the last 5 years. We do need to take advantage of data, not only because the number of publications is increasing. That graph looks a lot like a Wall Street graph of a few years ago before a monster crash. But a lot of criticism is often goes towards machine learning, but that's certainly not coming from me, because there's plenty of evidence that machine learning techniques provide a great tool for predictions, for data mining, for understanding, not yet, but I think we will get there. But they can also be used in hybrid types. They now come in so many types and shapes that they can really be used to feed the data. So let's face it, that predictions will improve if we improve theory, but also if we continue to improve our data banks. And obviously everyone is just probably thinking about estuaries at the moment, satellites, and how detecting shorelines of wet, dry edges for the case of estuaries, how important it is when we want to develop those data banks and share those data banks. We will get back to that. Here I just wanted to show very briefly some really nice work that an ongoing PhD student of mine is doing on using the machine learning for time series prediction. Is getting into the very complicated types of algorithms, dealing with convolutions, dealing with smart ways of training the networks, is dealing with the problem of what we want to optimize, how we want to optimize our training. And here, in fact, on the top plot, where there is time on one axis and shoreline position on the other, in black, you see the shoreline as it was measured. Then you see the result of, in purple, you can see the bootstrapping results using convolutional neural network. Here, the different structures of the network, how they affect prediction. And we still struggle a little more than a little bit with extreme erosion, those black lines that come down, but we're working on it, and I'm sure Eduardo will sort it out soon. And when I speak about the importance of data, I don't only refer to machine learning, I also refer to all techniques that deal with data, because data, time series in particular, I think they contain a lot more than we know, that we think. And in fact, Jennifer Montagno, a student now doing a postdoc in Toulouse, she used the complete ensemble empirical mode decomposition to extract the time scales that are dominant in the shoreline and in the drivers, the wave characteristics and also the weather characteristics, and then use those time scales, those patterns and those time scales to develop simple predictors of the future. And there's also work that, and I think Kristen Splinter is associated to it, that came out almost at the same time, that does very similar work. So we're, as you can see, the community is always pushing in the same direction. So what? Let's try to predict, and let's use what I call an R approach to prediction. I'm not saying that we should use R because it's probably one of the very few languages that I'm really allergic to. But let's use an R approach. We want our models to be reliable. We want them to work soundly in almost every situation. We want a realistic model that provides a good representation of the system of interest, which means it includes the relevant processes of the correct scale. So not all processes, but the processes that are relevant in my view. We want a model that is robust, so that has a limited parameter dependency. It's a bit of a dream, but I think if we build models at the correct time scale, we can reduce a lot the number of parameters. R ensemble, I think our work and what Kristen Splinter and Josh Simmons have just published show the importance of doing ensemble. Ensemble doesn't start with R, so I put an R in front and I call them reliable ensemble, because actually reasonable ensemble, because I want this ensemble to be a bit smarter than just an average. Maybe there are features that we can extract from some of the models that are to be kept more than others from other models, something that I think we have to work on. And then we can continue. I want the model to be revealing. I know it's not the best word, but I want the model to start with R. I want the model to make predictions, to enlighten, to help understanding, maybe even provide hints of what some sort of discovery. And I want the models to be rapid. Again, the word would be fast, but fast doesn't start with R. But this, I know it's also a little bit of a dream. We need to make, but we have to be ready to make a lot of runs. We need to be able to, we need to have models that we can run a lot, because there are a lot of sources of uncertainty, and the only way we can deal with them is statistically. I want the model to be reachable. What I mean with reachable here is really fantasy English, but reachable in the sense of being accessible. Let's make open models. Let's make open source model, open access data. We have to get better at this as a community. And yes, why not? I also want the models to be revolutionary, which I mean, I still believe that we can build models that will completely change the way we model the coastal area. But also let's be revolutionary in the sense that let's devise some community benchmark. Let's develop blind competitions. Let's try to look at this issue of long-term predictions in a variety of ways that question our ability to actually make predictions. And I realize you probably want something more practical and more focused than the R approach, and I'm really taking a lot of time. So I will just stress the importance of predicting the drivers, to address stochasticity in the driver, and to address the parameter sensitivity. The stochasticity in the drivers is a huge problem when we deal with long-term predictions. And then let's use ensembles and let's take advantage of data. And finally, a big, huge thank to the people I have the pleasure to work with. I'm sure I've forgotten some pictures. There are previous PhD students, current PhD students, people that work on estuaries, people that work on beaches, people from overseas, and it's a great community. And I think the one thing that is great about long-term prediction community is really that we all share a lot in terms of knowledge, data, and collaborations. Thank you all for your time.